What if I told you, a commercial airplane can fly higher than 40,000 feet, but doing so could push it dangerously close to falling out of the sky? At first, it sounds strange. Modern airliners are powerful, advanced, and built to handle extreme conditions. So why don't they simply climb higher, above the weather, above turbulence, into thinner air where flying should be easier? The answer lies deep inside the aircraft, within its engines, wings, and the invisible physics of the sky itself. Let's break it down. A commercial airplane typically cruises between 30,000 and 40,000 feet. At this altitude, the air is thin enough to reduce drag, allowing the aircraft to move faster and burn less fuel. But it's still dense enough for the wings to generate lift and for the engines to function efficiently. Because here's the first problem: air density. As an airplane climbs higher, the air becomes thinner, meaning fewer air molecules. And those molecules are everything. Wings depend on airflow to create lift. Engines depend on oxygen to produce thrust. Inside a turbofan engine, massive fans pull in air, compress it, mix it with fuel, and ignite it. This combustion creates the thrust that pushes the airplane forward. But at extreme altitudes, there simply isn't enough air. Less air means weaker combustion. Weaker combustion means less thrust. And less thrust means the aircraft struggles to stay in the sky. At the same time, the wings begin to lose their grip on the air. Lift is created by the movement of air over and under the wing. But as the air thins out, that lift decreases. To compensate, the aircraft must fly faster. But that introduces another problem. Speed limits. As altitude increases, the safe speed range becomes dangerously narrow. On one side, you have stall speed, the minimum speed needed to maintain lift. On the other side, you have maximum operating speed, where airflow can become unstable and damaging due to compressibility effects near the speed of sound. At high altitudes, these two limits begin to converge. This creates a narrow margin known as the Coffin Corner. Fly too slow, you stall. Fly too fast, you risk structural damage or loss of control. And at extreme altitudes, that safe window becomes razor thin. But that's not all. Inside the cabin, passengers are sitting comfortably, breathing normally, but only because the aircraft is pressurized. Outside the plane at 40,000 feet, the air pressure is so low that humans cannot survive without assistance. The aircraft pumps and regulates air to simulate a livable environment. But the higher the plane climbs, the greater the pressure difference between the inside and the outside. That difference puts enormous stress on the fuselage, the aircraft's body. Pushed too high, and the structural limits of the plane could be exceeded. Now combine all these factors. Engines losing efficiency. Wings producing less lift. A dangerously narrow speed margin. Increasing structural stress. And reduced oxygen availability. At some point, climbing higher doesn't make the flight better, it makes it unstable. So instead, aircraft operate in what engineers call the optimal cruise band. This is the altitude where fuel efficiency is maximized. Engines perform reliably. Wings generate stable lift. And safety margins remain wide. For most commercial airplanes, that sweet spot sits right below 40,000 feet. It's not the highest they can go. It's the highest they should go. Because in aviation, it's not about pushing limits, it's about balancing them. And at 40,000 feet, that balance is nearly perfect. So the next time you look out the window at cruising altitude, remember, you're not just flying high, you're flying exactly where physics, engineering, and survival all agree you should be.